Hello everyone. Today we are going to present our work on combining propositional logic-based decision diagrams with decision-making algorithms in urban systems. One of the most fundamental challenges in urban systems is how to coordinate the movement of autonomous or semi-autonomous vehicles while optimizing travel time, fuel, collisions, congestion, etc. in a partially observable environment with uncertainty. For example, for autonomous cars, we need better algorithms to coordinate their movements to ensure the safety of people. Another example is autonomous guided cars, which are used to load or unload cargo from a vessel or an aircraft and automatically transport the cargo to their respective transport vehicles or to warehouses. One more example is autonomous drones, which navigate the airspace of a region. Now, while coordinating such autonomous vehicles, the agents might also need to satisfy some constraints. For example, at an intersection, we might want to put constraints on the congestion level and distance between the autonomous agents. In warehouses, it might be desirable that the agents don't move in cycles to avoid unnecessary delay, save power, and optimize travel time and speed. Drones might have to cover some particular regions every k time steps for patrolling or surveillance purposes. A taxi might want to pick up passengers from a few places before dropping them off. So the main motivation for this work is how to incorporate domain knowledge or domain constraints with decision-making systems. To model decision-making systems, we use multi-agent reinforcement learning for multi-agent pathfinding under uncertainty and partial observability. The task is, given a map and a bunch of agents with their sources and destinations, those agents need to go from their respective sources to destinations while also satisfying some constraints. Some of the challenges that we tackle are sample efficiency, since the agent might take several simulations just to find a single feasible path, exploiting domain knowledge and combining them with RL algorithms. For example, we can encode the knowledge that the agent should not move in cycles or should not move on paths that lead them to dead ends, which would also improve the sample efficiency of RL algorithms. Another issue is of scalability, for which we hierarchically cluster our map to scale our framework to larger maps. In the left figure, we can see an agent getting stuck in a dead end, and in the right figure, the agent gets stuck in a loop. Here's the pipeline for our framework. We start with the domain knowledge and convert it into propositional rules. We then compile these rules to decision diagrams. Then we combine these decision diagrams with RL algorithms, which is our final framework. Now, how do we combine domain knowledge with RL? First off, while doing RL, we only sample paths that follow the constraints. In doing so, we are pruning the search space of all paths, which is combinatorial. Now for pruning the search space and incorporating the domain knowledge, we want to find a function called feasible actions, which takes in the partial path of the current time step and the source and the destination for an agent, and returns a set of next actions that are feasible, that is, they don't violate the constraints. We prune out the actions that do violate the constraints. For example, an action can lead an agent to end up in a cycle. During the training phase, we only sample paths that satisfy the constraints, resulting in trajectories that have good potential to generate high rewards. The information required to implement feasible actions can be compiled offline before the training phase. We'll describe this compilation in the next few slides. When we have this abstraction of feasible action set, we can do very simple modifications to deep RL algorithms to integrate this domain knowledge with them. For example, in policy gradient based algorithms, instead of softmax over all the actions, we just normalize the feasible actions. We just over the feasible actions. In Q-learning, we maximize the Q function only over the feasible actions rather than all the actions. This makes multi-agent RL algorithms more sample efficient and also improves their solution quality while explicitly combining domain knowledge. The first step in our framework for getting the feasible actions set is to encode the domain knowledge as propositional rules. We start with encoding paths as a Boolean formula. Given an undirected graph like this with 5 nodes and 5 edges, we associate Boolean variables with all the edges in the graph. If the edge occurs in a path, then the corresponding Boolean variables is set to true. Otherwise, it's set to false. Conjugation of all such variables represents a path, and disjunction of all such paths represents all possible paths in the graph. For example, in the given graph, the highlighted path in red from node n1 to n5 has the edge variables a, c, and e. So the variables a, c, e are set to true, and variables b, d are set to false. And the formula for the path looks like this: a and c and e, and negation of b and negation of d. Now we compile such Boolean formulae for all paths with constraints to decision diagrams. We use sentential decision diagrams, or SDDs, which in some ways generalize the well-known binary decision diagrams, or BDDs. SDDs are a more compact representation of Boolean functions, and the main reason for using SDDs over BDDs is that SDDs can be exponentially more succinct than BDDs. There you have an SDD. It is characterized by a full binary tree called P-tree, which in some sense determines its structure. It has two kinds of nodes: decision and terminal. For example, the circled part represents a decision node with the Boolean formula D and E, or not D and false. This node has two elements, DE is one and not D false is the other. The left parts of the rectangular boxes are called primes and the right parts are called subs. For example, D and not D are primes here, and E and false are subs. All the nodes with just a single literal are called terminal nodes. This figure has 2 children for each node, but in general it can have n children. We can also think of an SDD as a Boolean circuit where the circles represent OR gates and the rectangles represent AND gates. Now we can also extend the SDD to represent a probability distribution. For that, just parameterize each of the input to the decision node. For each decision node, the parameters form a local distribution, and all the parameters of the whole SDD give rise to a global probability distribution. Finally, to convert a Boolean formula to its SDD representation, we use the publicly available SDD compiler. More details about these decision diagrams are given in the paper. For the undirected graph in the bottom right, the SDD and the PSDD are shown. As you can see in the PSDD, the inputs to the decision nodes have some numbers on them, which represent a probability distribution. To sample a path, we start from the root node and select a non-zero probability branch until we reach the end, as shown using the red arrows. In this case, we can see that we select the positive literals A, C, and E, and negated literals B and D. So the sampled path is A, C, E. A PSDD also has inference methods, like finding marginal probabilities. Now, given that all the paths with constraints are represented as a decision diagram, to perform sample-efficient RL, we only sample the paths that satisfy those constraints. Given a partial path for an agent and an edge, we want to find out if the edge represents a feasible action. That is, the edge doesn't violate the constraints. For example, we want to ensure that taking that edge, the agent wouldn't end up in a cycle. For this, we leverage the domain knowledge that we have already compiled as a decision diagram. In a probabilistic sense, we want to find if the probability of an edge given the partial path is non-zero, which can be found using PSDD inference methods. But PSDD inference turns out to be quite slow while sampling paths in an episode of RL. To expedite this process, we develop a method to query the decision diagram which tells us if the probability of taking an edge given a partial path is non-zero. The idea is based on checking connectivity of two nodes in the decision diagram, the details of which are described in the paper. Our method improves the sampling speed and is much faster than PSDD inference. Also, to scale it up for large maps, we use hierarchical clustering, which we are going to describe in the next slide. These are the results for simulation speed in seconds of PSDD inference versus our method, called scans. And we can see that scans is significantly faster than PSDD inference. For example, for 5x5, Scans takes around 20 seconds to sample 10,000 paths, while PhD inference takes around 980 seconds. To scale up our framework, we use the idea of hierarchical clustering. The general idea is that we divide our map into multiple clusters. Also, we treat each cluster as a node and construct an abstract graph. So in this 4x4 map, there are 4 clusters, and the abstracted out graph is a 2x2 map with each cluster as a node. We impose the constraint that all paths inside all the clusters are simple. Moreover, the paths in the abstracted out graph should also be simple. So to sample a complete path from a given source to a given destination, we first sample a path across clusters from the abstracted graph. Then we sample a path within each cluster. This figure is an example of 2 levels of hierarchy, that is, a map is divided into some number of clusters. But we can have more levels, that is, each of these clusters can be further divided. This kind of clustering might discard a lot of paths because of constraints, but empirically it performs well on multi-agent pathfinding tasks, especially on large maps. We perform experiments on grid maps with various deep RL algorithms based on policy gradient and Q-learning. Grid maps look simple, but they can have a combinatorial number of paths between 2 nodes. For example, a grid as small as 10 cross 10 can have close to 10 raised to 13 simple paths. We test our framework on maps ranging from 4 cross 4 with 2 agents to 10 cross 10 with 30 agents. We plot the average total objective against the average sample count. The top row shows the results for policy gradient, and the bottom 2 plots show the results for Q-learning based algorithm. For example, the rightmost figure in the top row shows results on a 10 cross 10 grid. The red curve in the figure represents the average total objective of 30 agents without our knowledge compiled framework, and the purple curve is with our framework. We can clearly see that the purple curve performs much better in terms of sample complexity and solution quality. Similarly for other settings, RL algorithms combined with our framework perform better. Now here are the results of grid maps with some obstacles, like the shaded blocks shown in the figure. If the obstacle density is quite high, let's say 0.35, as in this figure, it's very hard for RL algorithms to find a feasible path in an episode. But when combined with our framework, they perform quite well. The left figure shows results for policy gradient algorithm, and the right one shows Q-learning. And we can again see that RL algorithms with our framework converge quite quickly as compared to the ones without the compiled knowledge. So in conclusion, we address the problems of decision making and pathfinding for multi-agent systems using reinforcement learning. We also looked at the applications of multi-agent RL for pathfinding in urban systems like autonomous cars, robots, and drones. We presented a framework that combined domain constraints with RL algorithms for pathfinding, which improves the performance of some previous algorithms, both in terms of sample efficiency and solution quality. Thank you.